The weird quantum world. Ever wanted to explore it yourself? You can do so with real quantum experiments. In this video, we will explain and explore quantum phenomena with regards to a device called interferometer and implemented using the quantum computer IBM Q. You can run those experiments yourself, as the IBM Q is publicly available and it's free. We will use a step-by-step approach so that it's accessible to everyone. Quantum mechanics and quantum computer programming for pedestrians. Our approach is like this. The interferometer will be depicted in this area. The implementation as a quantum program will be shown below. Mind that this program is not just simulating the quantum phenomena, but it's an actual implementation, as the underlying computer is a real quantum computer. The results of the quantum program will appear next to the program, and we will explain how to interpret these results in terms of the interferometer setup. For the nerds among you, I will also provide the underlying math, but it's sure safe to ignore this part, so don't worry. So let's start developing an interferometer, more precisely called a Mach-Zehnder interferometer. Imagine a laser beam directed onto a beam splitter, which is an optical device that splits a beam of light in two. The beam splitter will reflect half of the light, and half of the light will pass through. If we decrease the intensity of the laser beam, the situation remains always the same. 50% will pass through and 50% will be reflected upwards. But what if we send just one single photon, that is a single quantum of light, to the beam splitter? A single photon cannot be split in half by a beam splitter. Well, let's implement this scenario. First, we indicate the paths by the numbers 0 and 1. The input path used we call 0. We could have also approached the beam splitter coming from below, which would be input path 1. But for the moment, we can ignore this case. In quantum programming, a beam splitter is implemented by a so-called Hadamard gate. The terms are not important, but it's very important to note that a beam splitter and a Hadamard gate are really the same as far as quantum mechanics is concerned. The mathematical representations of a beam splitter and a Hadamard gate are exactly the same as illustrated in the math area. It's the mathematical operator used for quantum mechanical calculations. In case you want to learn more about this topic, I provided some links in the description, referring to online lectures of the MIT. In a quantum program, we are manipulating so-called qubits. We are starting with the 0 state. The symbol is pronounced 0-cat. It represents the entry path 0. H represents the beam splitter. The third symbol represents a measurement. In our scenario, the measurement will indicate which path was taken behind the beam splitter. If the photon was reflected and went upwards, the measurement will show a 0. If the measurement shows a 1, we know that the photon passed through the beam splitter and took the lower path. Let's run the program. As mentioned before, the IBM Q is a real quantum computer. Whenever you hit the run button, you are performing a real quantum experiment. In this video, we will also use the simulation feature, as in some instances it may provide more code flexibility and may avoid confusing glitches in the results. Feel free to play around with both of these features. For information how to access and use this quantum computer, see the links provided in the description. So, here's the result when shooting one photon. The photon took path 1. Let's run it again. This time the photon took path 0. Let's shoot a couple of photons one at a time. Shooting 10 photons, we see that 7 of them took path 1 and 3 of them took path 0. Now let's shoot 1000 photons one at a time. the result shows that 482 photons took path 0, 518 photons took path 1. Apparently, every photon is making a random choice. Looking at the math, you get that the possibility for path 0 is indeed 50%. The same for path 1, of course. To scientists, this inherent randomness of nature was quite a shock 100 years ago. Einstein expressed his disapproval of this explanation by his famous statement, "God doesn't play dice." To which Bohr replied, "Don't tell God what to do." Let's now finish the setup of the Mark-Zehnder interferometer by adding a second beam splitter to which both paths are directed using mirrors. Which results should we expect when measuring the exit paths of this second beam splitter? Well, a photon can pass through the first beam splitter, pass through the second beam splitter, and hit detector 0, that is, the display would show a 0. But the photon could also pass the first beam splitter and be reflected by the second one, hitting detector 1. It could first be reflected and pass the second one. And finally, it could be reflected twice. In total, we would expect 50% to be detected by detector 0 and 50% by detector 1. Let's run the experiment. In our quantum program, also the second beam splitter is just a Hadamard gate, of course. So the program looks like this. Mind that for the sake of clarity, I'm using the simulator function this time. Again, we shoot 1000 photons one at a time, and this is the result. The result is surprising. It's always 0. That is, entering the first beam splitter at entry path 0, all photons take exit path 0 of the second beam splitter. The usual explanation is that light is taking both paths, traveling as waves, which are interfering at the second beam splitter. This interference is constructive in the upper direction and destructive in the other direction. That's why we see all photons at detector 0. The math is backing up this result. When we run this experiment on the actual quantum computer instead of using the simulator, the results usually are less definite. This is because of unavoidable noise and errors during quantum computation. Keeping that in mind, the result is still quite clear. Nevertheless, it's often more compelling using the simulator function, as it guarantees the results are in line with the theory, avoiding irritating glitches. The state of the photon being in the upper and lower path at the same time is called superposition. But to be honest, this explanation seems very strange, because before we had seen that photons are either in the upper path or in the lower path. It's hard to imagine what is really happening to the photon. That's why we depicted the inner paths of the interferometer in dashed yellow lines. So why don't we peek into those paths in order to understand what is happening there? In real interferometers, polarization filters are used to control which path a photon has taken. But of course, any measure is fine. We could simply use the measurement symbol as before and put it between the two Hadamard gates. Currently, this can be done only in a pure simulator environment. That's why we will use another method, which can be used both in a simulation and in a real quantum experiment. It's the so-called C-NOT gate, which is a controlled NOT gate. Here is how it works. The little dot between the two H gates works like a detector. If it detects a 1, it will invert the value of the upper qubit. In our case, the upper qubit is 0 initially, so it would change that value to 1. If it detects a 0, it simply does nothing, and the upper qubit will stay 0. As a result, the information of the upper qubit reflects which path was taken. Let's measure this information. The result clearly shows that in fact both paths are used. It's exactly as we reasoned before. The photons sometimes are taking path 0 and sometimes path 1. But why then we saw this interference behavior with all photons exiting at detector 0? Let's move our measurement back to our interferometer and let's repeat our previous experiment. Oops, what's that? Suddenly we see the results we expected right from the start. Half of the photons reach detector 0, half of them detector 1. Also, this finding is backed up by the according math. But what does it mean? We have seen one of the big mysteries of quantum mechanics in action. Observing the path will change the behavior of the system. Mind that it's actually not really the observation itself. In our current setup, we are not even measuring the value of the upper qubit. Apparently, it's sufficient that the so-called witch path information is present somewhere in the system, even if we actually don't measure this information. In real interferometers, it is even possible to erase this information again and restore the interference phenomenon. This is called a quantum eraser. In our setup, we can do something similar. Looking at our quantum program, we see that the witch path information is stored in the upper qubit. When it assumed the value 0, we knew the photon took path 0. When it assumed the value 1, we knew the photon took path 1. This is because of the C0 gate and because the initial value of this upper qubit was well defined from the start. It was 0. If the initial value was a random value, this scheme wouldn't work anymore. The C0 gate would measure the path of the photon, and depending on that information, it would invert the value of the upper qubit. But inverting a random value is still a random value. The upper qubit would not hold the witch path information any longer. Let's implement this. In order to set the upper qubit to a random value before the C0 operation, we are using a Hadamard gate again. We run the experiment and the interference phenomenon is indeed restored. All photons are taking the upper exit again. To summarize our findings, when there is no witch path information, we see the interference phenomenon. When we measure the witch path information, the interference phenomenon disappears. When erasing the witch path information, the interference phenomenon reappears. Maybe in the math section you have spotted the term entanglement. Although it was not a necessity for reading the witch path information, the C0 gate will always entangle the two qubits involved. Entanglement is another most important phenomenon in quantum mechanics. It means that two apparently independent particles in fact are not independent. Their behavior will be correlated. Again, Einstein did not like it as a physical concept and referred to it as a spooky action at a distance. But today we know it's real. Let's explore it experimentally. A pair of entangled qubits can be produced by this setup. When measuring both of them concurrently and repeatedly, we always see them both as 0 or both as 1. That's no surprise. Although the H gate will create a random value of 0 or 1 for the lower qubit, the C0 gate will make sure that also the upper qubit assumes the same value. But when adding H gates before the measurement, we might expect both qubits to switch to a random value, as we have seen before. But instead, we discover that although the values are random, it will always be the same value for both qubits. Both qubits take the same random decision. The spooky action at a distance Einstein referred to is due to the fact that both qubits could be light years apart from each other, and they would still show this instantaneous correlation. Entanglement can be used to demonstrate an even more surprising witch path setup, using two coupled interferometers. If we had two interferometers using separate laser beams, then of course measuring the path in one of them will not change the state in the other one. In this setup, the interferometer below will show the interference phenomenon, but in the upper one we are measuring the path and hence the interference phenomenon vanishes. The implementation as a quantum program is straightforward. Mind, we are using the simulation feature this time in order to be able to measure the path directly, not using a C0 gate. Mind also that we are mapping the result of that in-path measurement always to the same classical bit as for the final measurement, just to avoid confusing result statistics. Looking at the lower qubit, that is qubit number 2, we indeed find the interference phenomenon. The result is always 0. Looking at the upper qubit, that is qubit number 1, we find both zeros and ones evenly distributed, no interference. Let's now feed the two interferometers with entangled photons by splitting a laser beam with a special crystal producing pairs of entangled photons. In our quantum program, we used the setup for entangled qubits as introduced before. When now checking the upper qubit, number 1, we see the evenly distributed zeros and ones just as before. But looking at the lower qubit, number 2, we now encounter that the interference phenomenon has disappeared. Evenly distributed zeros and ones also here, although we did not apply any witch path measurement. There is no more interference phenomenon in both interferometers. Because of entanglement, the witch path information is present also for the lower one, although no witch path measurement is applied. It appears that it's the information that counts more than anything else. That's why the renowned physicist Zeilinger is saying, quantum theory, correctly interpreted, is information theory. Our quantum program may not reflect the Mark-Zander interferometer setup in all details, but I hope that the approach was helpful to gain some insights into quantum mechanics and that you are motivated running your own quantum programs. Let us know about your adventures. Thanks for watching.